Good afternoon and welcome to the Carl Cymru for session number 1 for chemistry. This afternoon, session will be run by Miss Stevens from Browpedder School. The session will last 45 minutes where the teacher will go through the relevant subject content. If you have any questions, please use the question and answer section, which I will be in charge of today. My name is Mr. Black from Penglai School, and we will endeavour to answer your question during the session. This session will be recorded with the recording and any resources uploaded to the e-sgol website in the Carl Cymru area.
Good afternoon. The session, as the first slide outlines for you, and as will be available as the description on the Carl Cymru website, is going to be about just a bit of recap into your 10 content where you would have come across the standard ionic structure, and just feeding into the ion formation then and how that feeds into the initial unit for year 11, which I'm sure most of you are well into by now, which is the ionic bonding section, but primarily focusing on a skill that will be central to every unit you do throughout year 11, which is the Criss-cross rule and how you determine the ionic formula of any compound given to you. So just going back to the basics of what you've covered in year 10, just to make sure that you're comfortable and confident with that then. You can see the atomic structure, as I'm hoping you're all aware of, has got 3 central components to it. So you've got the central nucleus there, which contains positive protons and the neutral neutrons. So that is key to the understanding of the principle that ions form because of this desire of having the electrons that are currently circulating the nucleus to have a full outer shell. So that's just recap from what you did last year, hopefully. So the charge of an atom, as it says there, is always neutral because atoms, as they are, will have an equal number of both protons and electrons. So they, a bit like your kitchen scales, they will balance each other out really, where you have positive protons balanced out by those negative electrons. Okay, the neutrons, which are also present in the nucleus, doesn't really have any effect on the overall charge because of the fact that each neutron is neutral. Okay, so atom, and that is key here, is that you understand that this is the difference between an atom and an ion, is an atom will always have an equal number of both of them. Okay, so they cancel each other out, as I said earlier. Now that just outlines for you the expected recall of the atomic charge and mass. So it is a very, very tiny number you can see there for the mass of an electron, which is 1 divided by 1,840, but it's so relatively low, we just simply call it as 0 for GCSE purposes. So we assume that there is no mass really to an electron. You should also be aware it feeds into these ionic bonding section, and why ions form in the first place is that electrons, as they're orbiting those shells and or shells or orbits, they occupy certain areas and certain occupation of how much you can fit into it. So the first shell, as outlined there, holds a maximum occupancy of 2. So you can't fit any more than 2 electrons into that first shell. The second shell, as it says there, okay, can hold up to 8 electrons, and we assume for GCSE purposes that that extension of 8 will then be enough then to carry you through into the initial first 20, which is the maximum you're meant to know for GCSE. So we assume 2 in the first shell, 8 in every shell afterwards. Now, won't spend too much time on this kind of visualization, but I find it with my pupils, if you're struggling to get an understanding of this, I get them to visualize like a theatre or a cinema with like limited seating in the front row, and then if you can't get a seat in the front row, then you go to the next row and then the next row and the next row, because the front row is the best, as we all know. So if you visualize that, then it might be easy for you to understand what electronic configurations are by simply slotting them into visualizing your head seats in a cinema or theatre. Okay, so we always start from the inside and we work our way out. So if you're visualizing this theatre, you start in the front row and you work your way backwards. So the front row is 2 seats and then 8 in every row afterwards. So you can see there, oxygen has an atomic number of 8. Okay, so the bottom number in the periodic table have an 8. So how do you visualize how many electrons there are in that one? Well, because of the maximum occupancy of 2, 2 will fit into the front row in the sense, or the first shell. Out of the 8 then, there are 6, therefore, left over, and all 6 of those can fit in the second row because of the fact that it is a maximum of 8. So we say that it's got an electronic configuration of 2 followed by 6. So just to add on to that, the expected knowledge of what you can determine from that information. So you've got there 2, 6. From that, you can establish that it is in period 2, because there are 2 numbers. So the period at its core means how many shells you have occupied within that atom, or if you visualize it as the numbers that you write, like I did there, 2, 6, then you can assume that there are 2 numbers and therefore it's in period 2. Group is 6, okay? The group is always derived from how many are in the very last shell. So if you're writing it out, it would be the last number you write. And if you're drawing it out, it would be however many electrons, which we represent with crosses, how many crosses therefore you have on that last shell that you have drawn. So electrons, you have to be quite confident in order to build upon that knowledge in this 2, then 8, then 8, and what information you can establish from that. So you've got there a series of things that you might come across. What are they? Are they atoms? Are they ions? Are they molecules? So just so you're confident, atoms are single atoms of any element within the periodic table. So it comes as a singular one. An ion at its core means something that has lost or gained electrons, and the reasons why it would do so is something I'm going to cover now. And a molecule simply means atoms being shared in order, again, to try and achieve what will fundamentally be this ambition of having a full outer shell. Okay, so if you think about that, you've got the hydrogen there. It's a single atom, so it would slot in and be described as an atom. But if you look at the calcium, if you ignore the 2+, would be classified as an atom. But because it has become charged, it's become charged because of its loss of electrons, it is now not able to be described as an atom. You must describe it as an ion. Okay, molecule in there would simply be methane there, which is CH4, and carbon dioxide.
Neris, can I just stop you?
Yeah.
I can only see your the slideshow's not actually moving forward.
Oh, okay. Try that again. Okay, so that's irritating.
Yeah, so yeah, I mean, I can see the magnesium and fluoride or iodide, I think, and there you go, and now the PowerPoint's gone.
Okay, let's try that again.
So
hopefully it will. It's okay.
Can I also say, I think we're okay because we don't actually have any attendees at the moment.
Okay.
We watched after, so if we like, we could re-record. I don't know how you feel.
But then it'd be shorter. It'd be 10 minutes, and they're going to join the next. Oh, there isn't one after today, so maybe not. Can you see the slideshow now?
It's only showing me your. Yes, now I can see the slideshow. Yeah, so that's now presenting as a slideshow.
Okay.
I've got the red, yellow, and green slide up.
Yeah. Okay. So just to clarify, we'll just carry on because we've done nothing but recall until now. It should be fine.
Okay, that's fine.
If you look at the requirements then, so as pupils, we don't have an intermediate paper in science. You will be entered for a foundation or higher. So that just tells you that for foundation you have less requirements for recall, but those are outlined as you can see there. So making ions, and this is just to emphasize why ions form in the first place. So it's this desire and this ambition in a sense to achieve a full outer shell. So they're formed either by losing, if that is deemed to be the most straightforward and easy route to becoming full, or in some instances it must be easier in order to gain. So if you've got the metals on the left-hand side of the periodic table, they're on the left-hand side because they've got very few outer electrons. You've got group 1, that's called group 1 because it's got 1 outer electron. And then you've got the other side, you've got group 7, that's called group 7 because it's got 7. So if you think of it in the sense of group 1 being nearly empty, it's logical then to see that it's easier to lose the outer electron in order to gain that full outer shell. Group 7 on the other side would then be much more logical to gain an extra electron in order to get it back up from that 7 to the desired 8, and then they gain electrons. So an ion is all about achieving this full valent or outer electrons. Okay, so metal ions, you can see there that we've got sodium. Sodium is in group 1. It will therefore choose to lose that outer electron in order then to become stable. But if you lose a negative, as I'm sure your math teachers have gone on about it for long enough time, if you minus a minus in maths, you become a positive. So sodium, having lost 1 negative electron, becomes positive itself because you've got more positive protons in the middle than are left as kind of electrons being negative. There are less than there are positive protons. So it becomes positive overall as a charge. So where do they go? Well, as is the rule in life, you can't get rid of something unless something picks it up. So that has to be my favourite, or one of the most lamest chemistry jokes. Okay, so if you lose an electron, you become positive yourself. So non-metals do the exact opposite. So non-metals and metals are the best of friends in that sense, where you'll have metals happily and willingly giving up that outer electron, or electrons as it may be in group 2. And then you've got the non-metals that will pick them up because that is a way of getting themselves to be stable as well. So chlorine in group 7, best of buddies with sodium in group 1, and then it becomes, because you're taking on an extra negative, it becomes a negative charge overall. So you've got ions there, they're not beyond reason and of logic where they would stand. Group 1 will take on a positive 1 magnitude charge. Group 2, the same, it will lose 2 outer electrons, so it becomes plus 2. Group 3, it's still closer to being empty than it is to being full, so they will lose. And then you've got the flip argument, you've got group 5, which are closer to being full, so they will start to gain electrons when they react. Group 6 and 7 in the same manner. So you slot them in as so. So you've got the group 1 and group 2, 3 becoming positive because they will lose the negative electrons. You've got 5, 6 and 7 that will gain or take them on, becoming negative. Now you'll notice that there is a big fat empty strip for 2 locations. Group 0 is empty, and that is because they will not form ions readily, and neither will group 4. Now, I'm hoping that with a bit of thinking outside the box, you could come up with valid reasons why that may be. So group 0 is an easy one to take on because you would have covered that in year 10 where you did the noble gases. Well, they are filled to the outer most electrons in the outer shell anyway, so they do not need to lose or gain electrons because they've always got that stability of a full outer shell. But if you think about it, the other question is why therefore would group 4 not form ions as well? So it's the higher tier thinking that you'd need there. So if you're, as I said, we don't have an intermediate paper. If you're sitting a higher tier paper, then you should be able to rationale possibly why group 4 don't. Well, it is because being group 4, you're smack bang in the middle of being either full or being empty. So neither is easier than the other, and neither is very energetically favourable either. So it would be quite hard work for group 4 to lose 4, or alternatively to gain 4. Neither would be more beneficial than the other. So it doesn't do it, and it does it in a different way called covalent, where it shares, but I won't go into too much detail about that because there is a video on the Catalan website that was done at this point last year, which you can access and watch at a later point if that's something you'd like to do. Okay, so sodium chloride, as it says there, sodium will lose 1 and chlorine will pick that 1 up quite happily and readily. So magnesium chloride in the same sense, slightly more complex, and I'm sure some of you would have seen this if you've covered it already in your ionic bonding section. Magnesium needing to lose 2 will need to therefore pass 1 to each separate chlorine, and it forms a bit more of a complex product, which is 1 magnesium balanced out by 2 separate chlorine or chloride ions. So it brings me to the main purpose of this, and it's something that I can't go on about enough. It is central to your system of being able to understand why the formulas as they are. So ionic equations and ionic formula. So a common exam question is to simply ask you, what is the ionic compound aluminium oxide? What would the formula of it be? And you'll know from hopefully experience now of your teachers reminding you, you are supplied with a table of ions in any exam in the same way you're supplied with a periodic table. Okay, so you'll never be asked to memorize them. It's simply an expectation for you to be able to utilize that resource that's supplied to you and use it in the required way. So sodium chloride, for example, has got an ion of Na plus and Cl minus and has a formula of NaCl. Now, if you are quite logical, you might be able to work out that that's because 1 positive will be balanced out by 1 negative. So you only need 1 of each, okay? Aluminium hydroxide, a bit more complex because aluminium is charged by a positive by 3 magnitude, and hydroxide, which is even more complex because it's what we call a compound ion, because it's got more than 1 element involved in it, is negative by 1. It's slightly more complex for you then to understand how many we need to balance it out, but it is a case of 3 to 1, and therefore you need 3 of the singular to balance it out. So the formula to be AlOH3. That, however, can be really difficult to get your head around, and I appreciate that. Okay, so there is what we call the criss-cross rule, and that's what I'll focus on, which will then enable you to apply it consistently and be able to tackle such a question in any exam. Okay, so if you ask for any ionic equation for any compound, you should then, after this session today, be able to use that table of ions to apply the rules and work out what the formula is. So these are the ions you should know. Should know, yes. Memorize, no. So you've seen them hopefully before. So you got the metals then, which are called cations. They're positive charge. So they would be traditionally on the left hand side of the table given to you in an exam. And then you got the anions, the negative ones, which they're labeled simply negative. Don't get panicked by that word anions. But that's again something useful for the higher tier. They would be negative and they'd be on the right hand side of the table of ions supplied to you. So writing chemical formula then, the criss-cross rule, okay, and this is why I have to somewhat apologize because I have a stylus that doesn't want to work suddenly. So I just go to this pen, hopefully it'll work. If you apply the criss-cross rule, the boxes look complex, but everything I will explain to you as we go along. There are 4 key things that I'd like you to do as we proceed through the rules. Okay, so first thing, you write the symbol for each ion in the large boxes, and then you write the symbols and the charges in the smaller ones. So then you crisscross the numbers over, following the arrows as you go. There will be instances where you will need to potentially use brackets, but I will go through that when we get to such an example. And hopefully you'll become clearer as we work our way through them. So for example, if I go for, I don't know, let's go for aluminium oxide. So you would have in the aluminium oxide, you would have, where does it go? So if I put aluminium in there, excuse the writing because I have to do it with my mouse. And if I put oxide in there, O, okay, the charges would be 3 plus. Okay, and it would be 2 minus. Now notice the charges are outside those boxes because they will vanish. We will not have any charges present when we do this final product. So we'll take that 2, follow the green arrow, and that will go at the bottom So that 2 will come down to here, and this 3 here will come down and will fit into that there. If you keep the symbol where they were to begin with and don't interfere with them, don't start messing around with them, then in reality, you can then work out that the formula of aluminium oxide should then be Al, and we'll put the 2 at the bottom. Okay, and then you've got oxide, and then that 3 will come afterwards. So there's application of those crisscross rules. I'll take it through bit by bit. So I did it all on the first slide, but hopefully it'll be explanatory. So aluminium oxide, I'm going to take it through bit by bit again, so it's clear. The first step it tells you to do, if you look at it, write down the symbols for each ion in the large boxes. So that was the first thing I did, if you remember correctly. Okay, so I'm going to try and get my stylus to work, but I doubt it will play ball. But will it? No, it will not. It's gone on strike. So I did the aluminium there. The oxide would go there. Okay, that was the first rule. You put them in and they will stay static. They will not move from that position. Okay, so we've got aluminium there, we've got oxygen there. Okay, then put the charges in. So step by step, 3, and then we've got a 2. Okay, the second stage, okay, was then, if you remember, was to take the numbers down and put it into the box at the bottom of its neighbour. So I say crisscross from the top of what you have to the bottom of its neighbour. So it has to go from the top to the bottom, so it becomes what is described as superscript, which is at the top, but it will eventually end up being subscript at the bottom. So that 2 will come down to being there, and then that 3 will come down to being there. So that is a relatively straightforward example where there are no brackets required. It's simply a case of taking the numbers from the top and putting them literally crisscross. I do this with a class that's like I'm some gangster, so it's like crisscross from the top to the bottom, and that's as straightforward as possibly an example could be. Okay, there are, as is painfully the case in most things in chemistry, there are slight exceptions and slight tweaking to the rule that you will have to put into place. But if I then go through a certain amount of examples with you, hopefully it will become a bit clearer. Okay, so you've got aluminium oxide there with Al2O3. Emphasize again, I'm not hopefully repeating too much, but make sure that those charges do not appear in your final compound formula. Okay, so those plus and minuses will totally vanish. Okay, because the importance with forming this ionic compound is that the charges are cancelled out. So any positive ion, no matter how positive it is, will have to be balanced out and cancelled by an equivalent number of negatives then. Okay, so it's a case of any positives multiply to a point where they can be cancelled out by another multiplication of the negatives. Totally zero, totally neutral if you've applied the crisscross rule properly. So ammonium phosphate is slightly more complex. Okay, so with the example of ammonium phosphate, oh, go back, I pressed it by accident. Okay, if I think about the ammonium phosphate, the first thing to do, we'll go through it step by step there, is that you have to put in the ions where you want them. Okay, so the ions for ammonium, okay, it's a bit of a complex one because it is an ion of a compound, so it's got more than one capital letter in there. So in the case of ammonium, it is NH4. So we're going to put that in all, okay, within that, okay. It totally occupies that space within that box, okay. It is only positive by a charge of 1. And if you notice, scientists like myself are a bit lazy at times. We don't bother putting ones in. But if you're more comfortable putting that 1 in, by all means, there's nothing wrong with putting that 1 in. Okay, but if you don't see a number, don't panic. It's not like an error. It simply means there is 1 of that type. Now, phosphate is again a compound ion. Okay, so it has got the formula PO4, and it is charged by a negative charge of 3. Okay, so being that we are now applying a crisscross rule, and we have, as you can see here, we have a compound ion with 2 capital letters in, it is suggested then that you will put it in brackets before. Okay, so we're going to keep it in there, but we're going to incorporate brackets as well. So we're going to put the NH4 in there. Okay, and we will then put it in brackets so that we don't get confused by that bottom number, because I can appreciate that that bottom number 4 will throw a few candidates. Okay, and that's fine. There's nothing wrong with that. It's not something that you should judge yourself on. Just for like a safety net, maybe if you've got 2 capital letters, put brackets around everything, including that bottom number, so you don't get confused at the later point or the later steps. Phosphate will stay in that. Yet again, you can use brackets if you so choose. So let's put the phosphate in here. So we'll put the PO4. Because it is a compound ion, you can put brackets around it. It turns out in this example, you don't particularly need it, but I'll come back to what the requirements are and what the expectations are in a minute. So we'll take that 3 from the top and we will put it at the bottom here. Okay, you can take the 1, and if you're more comfortable with it, we'll put that 1 in there as well. There's nothing wrong with that. Okay, so if you then write out the whole, once you've applied it and you're confident that you've done it correctly, then what you can do then is rewrite the whole thing out in completion. So we can put the ammonium in there. We got the 3 at the bottom there, outside the brackets, not inside it. And then you've got the phosphate there that has the following formula, and it does have a 1 at the bottom. Okay, the reality is, if it's a singular, like in this case, you only need 1 of them, the brackets do become somewhat then, not pointless then, but unrequired. So what you can do is then you can actually take away the brackets if you're more comfortable doing so, giving you then the compound to be the following formula. So if I go on to the next one, you can see that you can actually write it without the bracket. If you are superbly kind of confident, then that's fine. Okay, you will understand why that brackets have vanished. If you're still not overly confident and you put in the brackets, so if you presented to the examiner the following compound, you would still get full credit. Okay, the examiner at no point will penalise you for including brackets if they're not required. Now, the counter argument is that they very much will. Okay, so if, for example, we presented it without these brackets here for the ammonium, so for example, if you'd gone NH4 without the brackets, so if I'd gone for ammonium phosphate NH4, and then just put the 3 there, without the brackets, and then put in the PO4. That is very much wrong then, okay? You must have the brackets around that, because it's the whole thing that is multiplied, not just the H, okay? So I do say frequently to both my higher and foundation pupils that if you are more comfortable including brackets, even when they're not required, leave them in, okay? You will not be penalised, and it's not a dangerous game then, but it can be much more of a negative thing if you get into the habit of not including them, and if they are necessary, you will not get that credit for the question. Okay, so I will encourage you possibly to always include brackets if that is something that you're more happy with and that makes the rules a bit easier to recall, because in exams you do get a bit panicked, as do all of us. So it might be beneficial for you to say, I'm going to include brackets even if I don't need them, because I'll still get the marks. Okay, now this is the secondary kind of sub rules, because you've got the major rules, which I put up earlier for you, but you've got the sub rule, and this is the major one. Okay, if the charges are the same size, only 1 of each ion is needed. Okay, so in simple terms, no crisscross is required. Okay, so the example would be things like if you've got, like you see so earlier we had Na plus for sodium and you have Cl minus, which means you got the positive one, you got the negative one. You'll only need 1 of each to make it 0. Okay, but in the same sense, if you have magnesium in group 2, Magnesium is positive by a magnitude of 2. Okay, so it will not need any sort of multiplication of an ion such as oxygen, which is also negatively charged by a magnitude of 2. So you've got 2 positives weighed out by 2 negatives. It's like if you think about old-fashioned scales, and they're not as common as they were, okay? If you think about old-fashioned scales where they were balanced out like a Libra symbol, if you think about it, if you've got 2 apples, balanced out by 2 apples on the other side, it doesn't matter. It would still be the same level as if you had 1 apple this side and 1 apple that side. So the charges, this is the sub rule you have to be very, very careful with, is that if the numbers are the same, in simple terms, the best way to think of it is no crisscross required. Okay, so sodium chloride is the example I put there for you. Because they're both positive, then it simply means that you push them together and it's NaCl. Calcium oxide, okay, so calcium is Ca2 plus. It would then, oh, see, that's a typo if ever there was one. Calcium chloride, that is. It should have been CaO. Apologies, I will rectify that and re-put it up on the resources in the correct form later on this evening. Okay, but it basically means that you would get any positives cancelled out by any negatives. Okay, iron 3 nitrite, you've got Fe3 plus, N3 minus. Okay, well that means you still only need 1 of each, so do not get thrown by this presence of this number. And that is something that is very common, is that they see the number and then and then they simply get thrown by it. So the fact that there's a 3 there and a 3 there does not mean you need 3 of each. Okay, you still only need 1 of each, and then that should be fine. Okay, so you have Fen, because that 3 charge on the ion being positive will be cancelled out by a single nitrite, which has got a negative charge of 3 as well. Okay, so let's just choose a random one. Let's see what we can come up with. Let's go for iron 3 oxide. Let's do this one, shall we? So iron 3. So to follow the rules, we've got Fe. Okay, and it's iron 3, and that's another opportunity maybe to tell you that you'll notice that in your table of ions, you do have 2 ions. I have to be careful with my Welsh accent saying this. You've got 2 ions for iron. Okay, so you've got the 2 plus, which means it would have lost 2 electrons, or you've got Fe3 plus, that means it's lost 3 electrons. Okay, the key thing there is to just look at the information given to you. They will, they will highlight for you whether they want it to be a 3 plus ion that's used or a 2 plus ion. Now you can see that in the question that it clearly states the Roman numeral 3, which means we're going to put a 3 in there. Okay, oxide is O. Okay, and then it is negatively charged by 2. So simple as it is, you keep those symbols as they are in the boxes. They do not get affected. Okay, but what we do is take this and we're going to take it all the way down, and we're going to put that then at the bottom. Okay, and then we're going to take this 3 and we're going to take it all the way down to there, and then put the 3 there. So as this whole concept then, the formula for iron 3 oxide would be Fe with a 2 at the bottom, and then oxide with a 3 there. Okay, so strategically just calm down somewhat and just take it bit by bit. Apply the same rule repeatedly, okay, and you won't go far wrong. So if I go on to another one, and maybe for the next one, let's choose something that's got a bit more complexity to it, maybe. So let's go for something that might require brackets, then that might help. Does that have any brackets required? No. No brackets required in any of them. But if I go to the bottom one then, to potassium sulfate, okay, so potassium is K and sulfate is SO4, Okay, sulfate is negative by 2, potassium is 1. Okay, I will emphasize again, you do not have to put that 1 in if you do not want to, but you're welcome to do so. If I take then that number and keep them, if I go all the way down, to up here and put the 1 down there, okay, and then follow the same, literally crisscross your work, okay, put the 2 down there. You'll notice that I've got a compound ion there, SO4, but I only need 1 of them. So the reality is you might not need to put those brackets in. If you're happy doing so, then do so. Okay, so as a whole concept then, you've got K2. If you're more comfortable, you can put, by all means, you can put the sulfate in there in brackets and put the 1 outside, if that is something you are happy with. If you're slightly cautious then about putting the brackets in, then you don't need that, you don't need that, you don't need that either. Okay, but if you include them, no harm done, because they will still give you that credit. Okay, so K2, SO4. Now, whilst I am doing this, it is probably an opportunity to remind you of the importance of size and location. Okay, so to do with symbols, they are very particular that you have the symbols at the right size. So they insist that a capital letter is the beginning of a new element. And for example, I know it's not the instance here, but you might already have heard of the magnetic metal cobalt, which has got the symbol CO. Okay, that is radically different when written to the compound that is carbon monoxide, which is also CO. Okay, so when you're writing such formulas as I have here, be very careful that you are clear where the numbers are and what size those letters are. Okay, so that you are confident that you won't be losing any marks by putting the wrong representation in. Right, if I go to something that is more complex and will require brackets, and without so will get you penalised. Okay, then if I go to, let's go to magnesium hydroxide. Okay, so we'll do this one in this slide. If you then take it to magnesium, small g, so be careful that it's not a capital G, it is a single element, so capital M and a small g, has got a 2+. Hydroxide is a compound ion again, OH, okay, and it is only charged by 1, so you can put that 1 in if you want, or you can't not, it's up to you. Okay, but what's important here is that when you represent them with the crisscross, you'll notice that there is suddenly a number appearing outside of it. So this 2, if you follow the path down this way, that 2 will go there. Okay, and then if you take that, then by all means you can put the 1 in, but you don't have to. Now you've got a choice then of how to represent that. If you choose to write it Mg, and then without the brackets you put the OH and simply the 2 there, because you've applied the crisscross rule, you put the 2 down there. The issue with that is that that 2 here will only multiply this final atom that comes before it. Okay, and that's not correct, because what you're trying to do is multiply the hydroxide ion. You're trying to multiply the whole thing. So in this instance, those brackets are essential. Okay, so it's a case of that is very much wrong. Okay, so you'd represent it with the correct use of brackets here as an Mg. Okay, OH. Okay, and then you'd put the 2 at the bottom outside, and that would then get you the credit. Okay, so that just emphasizes the fact that you've got this crucial inclusion of brackets sometimes. So as I said earlier, it might be beneficial for some of you, if you're more comfortable with it, to include brackets, even if you're not sure they're necessary, around the whole ion, including any bottom numbers or subscript numbers, just to keep yourself in the fact that you will get credit then. You will not be losing marks if you lose, if you put those brackets in and they're not necessary. So just to emphasize, another one then that possibly you do not need numbers for. Let's go for zinc carbonate. Okay, so if I go for this one here, zinc, okay, is Zn, and it's got a charge of 2+. Carbonate is CO3. Again, it's 2 though. Okay, so if you remember that kind of sub rule, we have now got 2 and we have 2. Now you do not crisscross. That is crucial here. So I often see as an examiner, because I examine this in the summer, is there will be a few candidates then that will put quite happily Zn2, and they will put in brackets quite often, so they kind of remember the brackets, but then misapply the rule and they put the 2 there. That is very wrong. Okay, so as an examiner can tell you, it's a very common mistake. So if you've ever done it, don't beat yourself up about it, but remember that little subs rule, which is if the numbers are the same, we don't crisscross. So in this case, it would be Zn, and then you put the carbonate afterwards. The use of brackets, because some of you might be more comfortable putting the brackets in immediately. There's no actual harm in putting brackets around it, even if you've remembered not to crisscross, which is the important thing here. If you put the brackets in around the CO3, still no one get penalised. Okay, so get into the habit of using these ions confidently, and that's the key thing that I wanted to get out of the way today in this first session, is that it's building your confidence in applying these. That's important. Okay, so in the case of Zn and then CO3, you do not need to crisscross. Okay, so writing chemical formula with the crisscross rule, then let's go for a final one before the time comes to an end. Let's go for aluminium sulfate maybe. So aluminium is Al3. You got sulfate there. There's SO4. Okay, and then it is negative by a magnitude of 2, by amount of 2. Now this does require crisscross. The reason you know immediately it does require crisscross is because these numbers are different. So you've got a 3 and you've got a 2, so we do need to apply the crisscross rule. The second thing to remember is this necessity for brackets, especially if the crisscross is applied. So let's just get ourselves into that immediately. Let's put the SO4 in so that we can apply that later on. And repeat, so at the bottom we're going to put the Al in. We're going to immediately put the sulfate in the required brackets. Okay, and then apply the crisscross rule. So this 2 is going to travel its way down to here, to the bottom. And then this 3 is going to travel its way down and go into this box here. So aluminium sulfate is quite a complicated looking compound at the end, but will then appear as Al. Just to be clear, there's no brackets required around the Al because that second letter is not a capital. So you only need brackets if you've got 2 capital letters, okay? I don't think I remembered to say that earlier. So that Al2 will come there, and then in brackets, you'll have the sulfate, which is SO4, and then you will require that 3 at the bottom, okay? So that is probably as complicated an example as I could have given you to finish you off on a Wednesday afternoon, but hopefully at least now you've got yourself a bit more confident in applying the rules. I'm sure I wouldn't be the first one that would have referred to as the crisscross rule, but all the same, seeing it in action repeatedly hopefully has helped you see it and why it's logical. Okay, so there are lots more slides, okay, all the answers. So I would suggest that you maybe challenge yourself. Earlier in the PowerPoint, I showed you the following. There were lots of questions, and in that screen you can see all the answers. So test yourself, maybe test a few out, see if you've understood the session today, and then cross-reference it with the answers on this slide. Okay, as I said earlier on in the first slide or two, I think it was, there are far more in this presentation than I ever intended to cover, some of which will be covered by Mr. Black in one of the later sessions this series. I think he'll be doing series 3 and lesson 3 or 4, but I've included it in this one so that those of you that are aspirational and you are aiming for that A star, A grade, then you can independently go through the presentation on the website, which can be easily accessed after this event. I'll upload the corrected PowerPoint later on tonight. I'm getting rid of that one error. Apologies for that. But hopefully after this session, then the higher tier aspirational ones, you can then take it further again and look at the other slides that are included in this presentation so that maybe you can get more familiar with things like ionic equations as well. Okay, so I'm hoping you found that useful. Apologies for the fact that we did have a few technical issues. It's out of our hands often that we can't do much about it, but I'm hoping that you found it useful nonetheless. So thank you.
Okay, thank you, and we'll see you next week. Bye.